my name is Brian Tay, and my FYP title is the study of quantum cryptography protocols for secure quantum communication. This project is under the collaboration with Professor Raymond Uy. Today is to give an overview of quantum cryptography and to understand quantum cryptography via simulation. To do that, we will first understand one-time pad, and after that we will try to understand BBM92 protocols. After that, we will look into the details of the protocols, which is the entanglement and teleportation. And after that, we will look at some of the simulation that I've done. Lastly, we will come to a conclusion. Let's try to understand one-time pad. Suppose I give you 4 totally random characters, and my question is, guess what's the word that is in my mind? Well, we come to the conclusion that it may be NINEM 9 or can be FIVE 5. But no, the answer is FOUR 4. So from this small experiment, we can know that as long as we have a totally random one-time pad, which is RBHI, you can theoretically create unconditionally secure cryptography. Now there's an asterisk here. Of course, what if it is not fully random? And secondly, for Alice, how will Alice send the one-time pad to Bob? So these are the 2 questions that we'll answer via quantum cryptography. Now there are a lot of protocols under quantum cryptography. One of it is BBM92. BBM92 starts with a satellite sending 2 entangled photons to Alice and Bob. And Alice is going to use these entangled photons, let's call it EPRA, and entangle it with a secret message that she wants to send. Let's say it's the message 4. And after that, she'll measure it. And her measurement will result in the classical message of 00, 01, 10, and 11, which Alice can use it to send it to Bob via optical fiber. Now something interesting happened here. When Bob received these instructions, this can be used as an instruction for him to transform his EPR pair such that when he measures it, he will get a message 4. And there you go. This is the whole BBM92 protocol. One of the biggest problems with the protocol just now is that how are we going to create 2 entangled photons? Well, one way we can do it via spontaneous parametric Dow conversion, which is essentially saying you have 1 photon going through a nonlinear crystal and the outcome is 2 photons. Well, of course, you need to obey some of the physics law, which is momentum conservation and energy conservation. Now, SPDC can be split into 2 types, type 1 and type 2. So both also will create entangled photons, but their difference lies in their nature. So how are they being produced? So their difference is essentially their difference in refractive index, and the difference in refractive index is due to the bump angle. Next, let's take a look at quantum teleportation. So we have obtained Bell state from the previous session, and these Bell states are actually the states of the entangled photons. Now Alice can use her pair of entangled photon and entangle it with the message state and measure it. And the measurement will give her one of the 4 possibilities of the equation here. Alright, and these equations can be used as instructions because these are classical message. So this can be used as instructions for Bob to apply Pauli X and Pauli Z matrices onto his pair of entangled photon. Alright, so once she measures his pair of entangled photon after the transformation, he will get back the message state. Now we have been talking a lot about measuring. So how do we actually measure the state? Well, can you do so using 3 beam splitter and 1 halfway plate. So by passing it through, you can get a value 0 or 1.
Let's look at a simulation for BBM92. We will start by importing the package project Q, and after that, we will define a function such that we can create the bell pair for Alice and Bob. After that, we will also define a function for Alice to entangle her qubit with the message, and after that to measure it. And we know that after measuring it, we get like 0, 0, 0, 0, 1, 1, 0, and 1, 1, and that number will be sent to Bob. So we will have to define another function for Bob to receive the message, process, and to measure it. The processing, of course, is the Pauli X and Pauli Z gate. So after that, we will have to define a function for the whole protocol. So we will have the input of Alice putting in a message, that's the input, and output is the Bob getting the message. Alright, so let's look at the hold the result of the simulation. So Alice input the message called 4, and after that she managed to transfer it to Bob, and Bob will measure it and analyze it, and the result is 4 as well. So we can conclude that the simulation is a success.
So this is the coding and the result of the simulation as iterated from the previous session. To conclude, a secure quantum cryptography is split into two parts. First, the preparation of two entangled photons, and second, teleportation. Now, in this study, we have not explored much of the practical sense of quantum cryptography, such as how are you going to prepare the single photon. But well, these issues can be left for the future study to explore. And with that, thank you.